what would be the bending stress, axial stress, then you can perform the structural limit state. Once you have done that one, the size of the pile is determined, the diameter, appropriate diameter. Then you can use, if you are going to use single pile, any diameter greater than that, you don't have to check it again for the structural ULS. So then you have to decide really what would be the length of the pile that you have to come up in the socketing level. So now you have to determine the ultimate shaft resistance, unit ultimate shaft resistance, FSU, which is alpha beta UCS. So you can get the UCS of the rock based on the CU equation that given over here, alpha beta factor that you already know how to determine it. And then also you can determine FBU. You can calculate that one based on Zhang's equation that we have mentioned also, 6.39 probably sigma CM to the power, is it 0.5 something, that FBU, check those equations, So this is the rock mass UCS. So when you get the intact rock UCS based on any lab test or correlations, you need to convert that UCS into rock mass by taking care by the RQD jointing of the rock mass. So once you have done it, then just follow the steps that we have taught you, the Pell's method, So get the length of the socket, the L max first, and that is the maximum length of the socket only based on the limit state load, and then you adjust the length to the design socket length based on the Pell's load sharing chart that we provided to you, that takes into account the deformation compatibility between the pile and the surrounding rock. So there is some sharing of the load is going to be at the base, but you have to ensure any load going at the base must be cleaned. No debris like soil-like material can be placed during the drilling at the base. You cannot rely on the base resistance at all. As a result, the strict guideline always you will be seeing in place to check the side of the socket as well as the base for any weak materials. If they are present, then your design must be adjusted, to account for those sort of weaker material, because rock comparatively provides very high resistance at the shaft and the base level, provided they are clean. And if any other material that is during drilling, this clay is coming and that is smearing the socket, it will significantly affect the resistance at the socket level as well as the base level. So this is the design. So your design task will be finding the diameter of the socket, finding the length of the socket, and also the settlement at the pile head. These three things, if you can do it, and we have given you the limitation of the settlement that can go, it's a 1% of the diameter. That means if it is a big diameter, rock socket piles normally very big, it's probably 750 onwards, it can go even up to 1.82 meter. Even sometimes people are using barrette. Barrette means it's a rectangular section of the pile is a rectangle, very big. It could be like 2.8 meter by say 2.5 meter or 2 meter, around that. A very big rectangular section of the pile. They use normally very high-rise building. This sort of thing is a special equipment drilling technique you have to design. They normally, like for Dubai, those big tower, like a kilometer high tower, over here, there you'll be seeing this sort of load, where the load can go up to 80,000 kilonewton or 80 meganewton, around that. It's a huge load, and the pile can go in rock very deep, so because it's a very huge load. It can go up to 80 to 90 meter long pile, that big size, So that is not our issue. Our issue is now very small load, 8,000 kilonewton load, which is very comparable the load that you are dealing or the towers that you are dealing with. So you can now solve this with our help. So any questions? You have got any questions to ask me before you go and start this solution? And I like to see that every one of you are doing this solution, because this is embedded in task 2, and I don't like to hear so many questions once we finish this task. Then once you are going again to complete the assignment 2, again you are flooding with questions, So you need to really put your time, this 2 hour, in such a way that you are learning this full design, and you can execute that in your assignment number 2. So we cannot have, it's almost like a trial you are doing. We did in the practice class. In the lecture, we have solved one problem. Then we came to the practice, we are solving another problem. We didn't have the negative drag down in the lecture because it was sand before, but the rock was identical. Now we change that one to negative skin friction, and you just need to apply these 2 knowledge in your task. There is nothing can be easier than this. So please feel free to do that over the next hour at least with our help, and execute it to the end. Any questions?
Asad,
Yes.
you said to design for the diameter, but in the problem, the diameter is already given as 1 meter, right?
Yeah, but this is given. I am giving to you, assuming that we are checking so many times this diameter structural ULS. I do not like to see that, well, you have to check it again, but in real design, you have to find that diameter, isn't it?
Yeah, so for this practice set, we don't need to find it, but
You
for our
don't find
task
it,
2,
but
we
you
do.
try to check it, Shing. It's better
Okay.
to check that whether that is meeting structural ULS or not.
Okay.
Otherwise, when you are executing your assignment 1, assignment 2, you started to go for like a 1 meter diameter, but structurally it might fail, isn't it? So it is good, although I have given you 1 meter, but I didn't say I checked it already. Nowhere
Okay.
I am saying that I checked it. So you can check it whether that 1 meter is satisfying the structural ULS or not. But if you like to go like an exam environment, if I asking you the diameter is given, and I'm not asking you to check for structural ULS, then you immediately go to the second problem. You don't need to do that.
Yeah.
Okay.
Okay.
Basically, we are looking at the design task, full design task. So that 1 meter and the FC prime that I have given, whether that satisfies that requirement of the structural ULS or not, it is worthwhile to have a look, because that you need to execute in your task 2. Make sense, Shing? Any other questions? Okay, then I'm going to divide you into 3 groups. Around 16 you will be having. So 6 people per group. So we'll go again 3 rooms, because we have got a specific task to do, and then we work on that. Options, 60 minutes. Yes, that's fine.
So does anyone know how to get started?
Not quite.
Which part were we doing again for room 1?
Not sure. Let me double check.
We're doing the shaft and base resistance.
Alright.
Yeah.
Shaft and base.
But I think he still expects us to do everything again.
Yeah, I'm sure.
So I guess we can start with the structural ULS thing that Asad was saying to see if the diameter is adequate.
Asad,
Yes.
I just have a question. For
The
this,
question.
so for this, when we're checking the structural, like, just for the load, are we always using the unfactored load?
What we did before?
Unfactored.
What we
I
did
think
before, you remember
we-
structural ULS we have checked before, isn't it?
Yes.
It's 1.35, and then for the negative skin friction it's 1.2.
Yes.
Yeah. Okay.
I think, Shing, always it would be good, like when you are talking like this, I really feel very uncomfortable. I like to see you guys, face to face. That is something I always appreciate, and also, when you are, doing things, it is always expected. We should be drawing, and we'll be writing on the board, and that is expected, like when Joanne is asking that question, Singh has answered that question. I mean, it's okay. I know that answer is right, Shing, but how would you explain to your peer? That is the thing we should develop over here. Like, it's easy for Shing, you explained it very easily, but Joanne asked that question. And when we go, and we have done it before in the pile design, this is not the first time we are doing. So rather, I think we should pull a whiteboard and try to write over there. So you just show me that you are able to share that knowledge, Shing. Yeah, that's the thing I like, Shing. Yeah, that's the good thing. So now, yep. So explain to them, what everybody that we should learn each other. That is the best place, basically. Yep.
So I did this initially without the negative skin friction because I forgot about it.
I can see
But
that.
then, so basically, this is what we did in the previous.
Previous pile design.
Yeah. So like it's just for the combined load factor we use 1.35, and then for the skin friction we'll be using 1.2.
Shing, if you don't mind, like, why don't you draw something like this? So this is our pile. This is our pile. We have got, this is our 5 meter, the subsoil, and then you have got rock. And so this is 8,000 over here. And so our positional tolerance could be anything, as we mentioned before, 75 millimeter. And this is the section where the negative drag down, which is causing the pile to subject the maximum stress. So now people can see it, how this has been translated, this one. So this part is coming basically the compression on the top and the positional tolerance due to the bending. So that is the bending stress, and that is the compressive stress that is developing. So you have got multiplier 1.35 because that is the combined load factor. Then we know that for negative drag down, we have a load factor of 1.2, almost identical. Remember, that is close to your dead load. And then you multiply with your maximum negative drag down, because that is the place the negative skin friction will be gradually increasing with the depth, so at that point it will be the highest. So to get that maximum drag down, you have to calculate that what is the value you are having, and this negative drag down he is calculating basically based on the drain properties, which is C dash and phi dash of the soil. Yep. Now explain. I am not going to explain. I'm going clearing this one.
So in the problem sheet, you've given us a lot of information already.
Can anybody tell me how much would be the negative skin friction? I think you know. Shing, I think you know. Matilda, can you explain?
How much
Can
would
you
the
can you explain this one? I know that you found a little bit difficult to get the average shaft resistance in the midterm,
you remember me.
Yeah, oh, definitely. I remember all of you.
I kept on getting 27 instead of 30, so I was
probably
confused.
that's okay. Yeah, that's not bad. Still, that's okay. But I like to know, how you do explain that one. I think, Shing, you could have left your the workout over there, and Matilda could have used the annotation, on the top, and she could have showed us, Can you tell me, Matilda, how would you get that negative shaft resistance for the top weaker layer.
Oh dear. Wait. So do you want me to like
You can annotate
annotate?
it over here. You can annotate over here. Go on the top.
How?
Go on the top and select
Oh.
annotation. No, there is a
Yeah.
on your top of the screen. If you see that when you are
Yes.
seeing, you are viewing screen, view option. On the top of your screen, there is a
Yeah,
view option.
I found it.
Under
I'm just-
view option,
yeah.
under view option, just on the top.
Yeah, I found it. I have the
Now you can show. Yes, please.
negative skin friction.
Yes.
Let me go back a couple of weeks and find the slides for it.
I can help you. You don't need to go to the slide. Don't go and get that far. We don't need really. This is really the one that we are looking, the pile, and this is the negative part we are looking. It's a 5 meter.
Yep.
We have given really the soil CU value, and we have given CU 15 kPa. We have been given, and then phi dash is given is 20 degree friction angle, and we also given you the sigma dash value. I think over here probably, I think we can look at that one carefully. I just probably will emphasize a little bit over here. So how do you go with your negative skin friction? What equation that you use? So the first principle I am asking you, we know that when you try to get the positive skin friction in clay soil, we use the alpha method, alpha CU, isn't it, Matilda?
Yep.
But when we try to determine the negative skin friction, which works other way, what is the principle that we use? What type of properties that we use here? Is it a drain properties or undrained properties?
I would say drain.
What is the reason?
I'm not sure.
Okay, because the concept associated with undrained and drained, are you clear about that?
Yeah, I suppose.
How do you explain undrained condition?
In a cohesive soil,
Yes.
undrained is sort of like the short-term effect, I'd say. So
Yes.
the pore pressure hasn't dissipated yet, and undrained is drained is the long-term effect.
When it's dissipated.
Yes.
So if you looking this negative shaft resistance, which is working on the clay, and that reverses this the resistance downward, what is the phenomenon that time is happening? That means the soil is moving downward that moment. So
Yeah.
soil is moving downward, and then it's pulling the whole pile around the skin downward. And that happens basically through a process known as consolidation. And if consolidation is happening, that time we call that is a drained, consolidation is a drain phenomena, isn't it? Soil consolidation takes place because of the dissipation of the pore water pressure. So that is a drained phenomenon. And if it is a drained phenomenon, we have to calculate this down drag, we have to use the drain properties. That means the frictional properties would be very important. Okay, now how do you calculate that one? If it is a frictional material, how do you calculate the resistance around the shaft? What equation that you should be using?
I would use the that's the eraser.
Similar to the sand.
Sorry, I'm trying to change it to drawing.
You
Alright.
can.
For sand or for clay?
Because it's a drain properties of the clay is behaving similar to the sand material. Sand always behaves like a drain material.
So like this equation?
Yep, correct. Yep. So you are going to use that is the down drag, which is causing the pile, pulling downward. So now I think, Shing, can you tell me when you have got K value is already, it's coming the earth pressure, because this is like a board pile case. It's a board pile case. And when you are doing this board pile, you definitely have to have a support, because if you do not have any casing and there is a soft soil, the borehole is going to collapse. So the earth pressure, basically we can take, literally K over K naught 1, because we are not letting any soil to move towards the hole. Am I right, Shing?
I just use the K over K naught ratio that you put in the practice.
Yeah,
set.
0.8 is okay, but 0.8 to 1 it can go.
Okay.
Yeah, but it will not go beyond 1. So because what is happening, if you remember that, what we are doing over here, so this is the ground. If we are excavating the ground, you have to put a steel casing around the hole, and you push this steel casing around the hole so that the hole is remaining stable. Otherwise, this soft soil is going to cave in. Your hole will be collapsing. So if you have got steel casing, you are pushing it down to the soft soil. That means the soil is not allowed to move towards the hole at all. So K naught condition, almost we can say it can prevail. Because soil is not allowed to move, that means at rest condition. So now you can drill, hole through that one using your rock roller, that coring bit, and slowly you can go into the rock. Now, well, that is known to you. Now, this sigma V dash. What is the value of the sigma V dash that you are going to take into account? That's the effective stress in the middle of that settling layer.
Yep.
So what was the depth? We have 10 meter. So 10 meter is half of that is 5 meter. Because we are trying to calculate the average shaft resistance, so we can take the depth as half of that. The one thing I must say, Shing, this is the place I must say that if we see a soil is very soft, a soil can be only soft once there are lots of water in there.
So we assume that the water table is at the ground level.
It is probably, because otherwise soil cannot be soft.
Makes sense. Okay.
Yeah, clay cannot be soft, although we haven't mentioned it. But when I say soft soil, our design probably we should assume it is probably implied that water is too much water in there, water content is very high.
Yeah,
so we can assume that one. Because it's a clay is very soft. Assume water table at the ground level. That is implied. So now you have deducted that one. It's not a big value, but still you will be seeing there could be a significant value because the pile will be very big. Now, okay, yep, you have gone there. So you put maybe that one times 1020. So that will give you whatever the value is coming. So 5 times, it will be very tiny value.
Got 6.8.
Okay. What is the value?
Yeah, I got 6.8 so.
6.8 kPa. Then you know now how to apply that ULS, structural ULS now. So you go back to your Pmax here twice pi d, if you can get the total value over there.
Oh yeah, if we assume that D is
So the
unknown,
total
then I
load will
just
be, you assume maybe 1 meter if you think. Yeah, assume for the trial you can go 1 meter and check whether that 1 meter is good enough or not. Doesn't make any difference. Either you make it unknown or make it known. Assume D is 1 meter. And then check left hand and right hand value. Yeah?
Yeah. Okay. Yep.
And then once it is done, that structural LL, ML, ULS. The load looks very high.
I don't know if I'm doing something wrong for the negative skin
Because
friction.
the negative skin friction, it looks to me a little bit high.
You're
Yeah.
multiplying by 2. Why is that? Shing?
Twice pi d. So it's not 2, it's a twice pi r. Shing?
Oh yeah, it's R, not D.
Yeah, not d. So it's a pi d or twice. Yeah, that's the one. So
This
twice
is the
pi.
perimeter.
Yeah, that's the perimeter. Yes, correct.
So like,
So 2 into 3.14 into 0.5 into 10 into 6.88. That will give you 216.
is that very high? Is that like a
No,
okay?
no, that's okay. The value before it was very high. You mentioned 400 something, you know.
Yeah.
So now it looks okay to me. So now you can look at your structural ULS. You can plug in that value and you can check left and right hand side. Yeah.
Yep.
So that is the value. So Shing PNX, that is in kilonewton. Where is your A?
Sorry.
Shing. Where is your A? PNX, this is in kilonewton, remember?
Oh, no wonder. Yeah.
Yeah. That is in kilonewton. So that should be divided by pi r square.
Yep.
Yep.
Okay. Got it.
Small thing, we always do mistake. Seeing this one is right or wrong? Pi d4 by 64 from my memory is I for circular section.
But it shouldn't matter because like the D is 1 anyway.
Yeah, it is not matter, but but
Oh,
if
but I
you
got
write
it
the wrong equation, that matters, you know. If it is
Sure.
0.9, 0.8, it matters.
Yeah. My bad.
Yeah, it should satisfy, I'm pretty sure.
Yeah. Definitely satisfies.
Yeah, so that's okay. Now your 1 meter diameter, so I think always I feel Shing, you know, and all others, you know, when you do this sort of unknown trial and error, it is always good to start with a value rather than, you know, trying to solve a quadratic equation or a 3-degree equation. That becomes so cumbersome. I thought always you start with a non-diameter and try to see right and left whether it's satisfying or not. And if it is satisfying, you don't need to refine in the exam environment. But in the design environment, obviously, it is good to refine it, okay? But in the exam environment, if it is satisfying, there is a big margin still there, well, you start carry on.
Okay.
Make sense?
Got it.
Yep.
Yeah.
So that is done now. You have got that one. Now you have to go in the second one. Get your FSU, the unit shaft resistance. Yes, that one already you have done it. Yep. Probably you can explain to the other people, you know, how you have come up to this point. You have done it, and then you would be able to solve this one up to the end, isn't it, Shing? I guess you
I
can
hope
explain to your group. It looks like I will be coming back because I can see you have gone really far, and some of this value you need to refine because UCS probably will be changing. This is 8% moisture content. Did you use 8% over here?
Yeah, I did.
So it's okay. So if you use 8% moisture content, you have got it already. Try to share this one with the group, and then I will be coming back. Okay?
Okay.
No worries. I'm going to leave your room and going to join in room number 3.
Thanks, Asato.
Do you guys know if the relationships that they gave, are those log values base 10 or base E? I can't remember.
Base 10, I think.
Base 10, yeah.
I assume they would use lin if they were doing base E,
Yeah.
like ln.
Hello.
Hi.
Hi.
Hello.
How are you going?
Okay.
Okay.
Okay. Any problem yet? No?
I think we're
Yeah, just asking.
all right at the moment. We're all kind of just following the week 9 Zoom lectures.
Yeah.
I have a question.
Yeah.
About the settlement. Do we have to consider like the elastic shortening?
Yeah, elastic shortening you have to find. You must find.
Okay.
Yeah.
And that's
If you ask in the file head settlement, then that settlement of the rock socket plus elastic shortening.
elastic shortening. Okay. And that's because of the clay layer on top, right? Because
Yeah.
Okay.
The top part is subjected to the elastic compression.
Yep.
On that 8,000 load plus negative skin friction.
The skin friction. Yeah.
Yep.
Wait, so the del V formula is just using the 8,000 kilonewtons, and then we have to use a separate one for.
We can use that SC1 from that
formula.
Yeah, SC1. Yeah.
Yeah. Okay.
Oh, okay, got it.
Just the PLOA.
So the P in that case is just the negative skin friction.
Isn't it plus?
Yeah, plus 8,000 you have to consider. No? Pi top, the 8,000 will be applied.
Okay, I get it. I got it.
Yeah, I got one problem. Is this rock is the fractured rock, or is there any fractures on your problem? Is it fractured or not? Are you given any joint frequency or something like that in this problem? No.
No.
Sure. If you just see the figure, 5 joints per meter, no? That means it's not a unfractured rock. That means unfractured rock means the intact rock. There are no fractures. Okay, the thing is the parameters that Young's modulus you are calculating from that Hughes formula, it will be an intact parameters. Okay, then you have to convert that intact parameters into the rock mass parameters. Or else you can assume that one as rock mass to intact ratio is 1, or else for your simplicity. But the correct way is in your project, I think you have to do that one. I think in the mastery article section, you will see a paper called Mustone Rock Modulus with Joints. If you open that one, then you will see a graph by Williams. Well, the x-axis of that graph will be the joint frequency, and the y-axis will be the rock mass to rock intact rock modulus ratio. I'm talking about this chart. This one.
Yeah.
The x-axis will be joint frequency. This is the mass factor. EM or EI. EM is the rock mass. EI is the rock modulus. For your case, it's 5, no? For 5 is nearly 1. So have find the correctly the value is 0.95, the correct value. This one you can find in the mastery radical section. This graph.
Do we use this mass factor just for the modulus of the rock?
Yeah,
so like,
yeah. Only for the elastic modulus of the rock.
And then that is applied for all our calculations or just for the settlement?
If you take in that EP over ER ratio, it will affect, no?
Yeah, true.
Everywhere. Yeah, everywhere.
Okay.
Because you are not now dealing with the intact rock. Your rock is fractured. You are dealing with the rock mass.
So whenever there are any joints, then we have to do this.
Yeah, you must follow. In a project, you see a lot of joints, no? In that pictures, in the core boxes, then you must follow this one in a project.
This was in Williams, is it?
Williams, yeah. I'll show you the place. Then it's easy, no? We just go to model. If you go to the mastery article section, I'm talking about this paper, this one. Okay.
Yep.
So click here. You will get the chart. Okay.
So this only affects the socket length, right?
Yep.
Okay.
And the settlement also. In the settlement part, you in the bottom, You will have the rock modulus you need to insert, no?
Oh, yeah.
Yeah. Matilda, any problem? Okay.
Should we be finding FBU as well, or do we just find FSU and then?
You have to find the BU also, no?
Okay.
Because this you are optimizing the pi rock socket length, no? Using that chart. If you are doing that one, that means the some proportion, a small proportion of the total load will go to the base as well. Maybe less than 10% of the total load. FBU you can find using that the Shanks equation, that 6.39 into sigma cu into 0.4 to the power 0.45. This equation.
Yeah.
Shing,
Yeah.
I got one problem. How about the geotechnical reduction factor for this kind of rock socket pile design in Melbourne area?
0.75?
Yeah, 0.75 if I'm managing a very low risk, no? Usually you are using 0.5 or something like that, no?
I think Asad said because we know Melbourne mudstone very well, we can use 0.9 or something.
Yeah, but the thing is, the properties of the Melbourne mudstone is varying to less to place also. I think in this Melbourne area, the geotechnical engineers are practicing for this kind of a rock socket pile design, geotechnical reduction factor of 0.65. The 0.75 people in Sydney using. I think they got the sophisticated instrument, those things. In this area,
But how would we know? How
Sorry?
would we know what? How would we know what reduction factors to use?
It depends on the geography. Depends on the area. In this region,
So
it's 0.65 for rock socket pile.
Okay, then when Asad said like, oh, because we know the properties very well, we can use a higher factor. Is that for something else?
Yeah. If you are really confident, then you can go for 0.75. And your testing facilities are highly reliable.
This is 5M,
I think
right?
it's better to go with the intermediate state. Then you are getting low risk to high risk in the middle.
Wait, this is for the ULS geotechnical
ULS, for geotechnical ULS.
What about for the SLS?
SLS, no safety factors, no?
Isn't there like a 5M?
Isn't there the point?
The thing is, if you are designing the rock socket pile according to the Spells method, the settlement is always less than 1% the pile diameter. Then serviceability always will be satisfied. Then in this problem also, if you are finding the final settlement, the pile diameter is 1 meter, no? That means your answer should be less than 10 millimeter altogether. You'll get 10 millimeter definitely if you are using that method.
Okay, got it. So after we find FSU and FPU, we just multiply FSU by the perimeter multiplied the length, and then that will give us our FSU. And then the FPU we multiply by the base area.
Yeah.
And then we take 1.35 and divide by 0.65 to give us our factor of safety.
Yep.
Got it.
So
Okay.
Your project is due on next week, no? The next one.
Hello everyone, this is Asad making a short presentation on the design of rock socketed pile to assist you completing the parts loads often larger than depending on the pile head settlement of a rock socketed pile. The pile is a 660 mm in diameter and socketed 1.8 meter in mudstone, which gives a length to diameter ratio about 3. As can be seen, the side load reaches the peak value at a very small displacement, approximately at 1% pile diameter, and thereafter it almost remains unchanged with displacement. But the base load gradually increases with the pile head displacement and reaches about 5 meganewton at 10% diameter, which is considered to value about height of a pile. Length to diameter ratio from 1 to 4 were investigated here. For length to diameter ratio 1, almost 50-50 sharing of load between the base and the shaft.
Hello, Pam. Are you okay with the design?
Increase of socket length to diameter ratio, more loads transfer to the side shear. For length to diameter ratio of 4, almost no load is observed to go at the base. This shows that if we want to design a rock socketed pile for base and side resistances, then the socket length to diameter ratio should be less than 4. Also, smaller rock modulus contributes to higher base load transfer, as has been shown for L/D ratio of 3. Note, more dependent on the base load is associated with large pile head settlement. The figure here provides load distribution for rock-socketed pile with increased relative stiffness value K, which is defined as the ratio of the Young's modulus of the pile and rock material, and rock socket length to radius ratio L/A. An increase of A value indicates a decrease of rock modulus, which contributes to an increased base load transfer. Note, the x-axis extends up to a socket length to radius ratio up to 8 or length to diameter ratio of 4. The ultimate load capacity of a rock-socketed pile, as per the ultimate limit state design method, is the sum of the ultimate load at the base and around the side of the socket. Side resistance of soils is neglected. The base and side resistances of rock-socketed piles depend on the quality of the rock mass, which is a function of rock.
Anyone find the socket length for this problem? Not yet.
The what length?
Length of the rock socket? Yes.
Into the rock, is it?
Yeah, into the rock. Yeah.
3.1. I don't know if that's right.
Axial compressive strength, defective spacing, presence of claying field.
Yeah, applied load is
This
8,000
information
something like
which
that.
can be obtained from the core load
Yeah.
are vital for
8,000.
determining the ultimate side and base resistance of the
I
pile.
can just do a rough
As
approximation.
mentioned earlier,
8,000 you have to multiply the load factor 1.35 plus the negative distribution is how much? Sorry?
260.
Plus 1.2 into negative distribution. The force, I just want to know what's the force.
the
200
pile
newtons?
can be designed based on the elastic principle.
K and tan
This
delta.
is a linear load
Sorry?
216.
216, yeah. 216. That will be the total factored load will be 11,000 11,059 kilonewtons. Okay. By assuming the 100% shaft, that means all the total load, all the ultimate load is taken by the shaft. I can find the initial length. Okay. 11,000
Did we only consider the rocks, the shaft?
Sorry, Robert.
Is it just the rock socket shaft that we use? As we don't use like the first 10 meters of soil as part of the shaft?
Yeah. In this case, you are relying on the rock socket, not the soil. Okay. Then you have to divide by the.
Got like 9 meters of rock length. Like that's
It's too big, no?
Is it? I don't know.
Yeah. I'm just finding 5 into your diameter is 1 meter, no?
Yeah, 1 meter.
1 meter. Then what was the FSU value?
I got 880 something.
Just megapascal value. I'm just asking.
Mine was like 600-ish around there.
600 kPa.
Yeah.
That means the 0.6 MPa, no? Then answer will be I'm just getting 5.8 meters nearly. Okay, this is the way I have calculated. Okay, I can show you. Then it's easy, no?
Wait, how do you get your FSU so large? Mine's only like so small. Mine's like 900.
Yeah, the thing is, I just need to multiply 1.35 into 8,000 plus 1.2 into 260, as Jani said. This is the total load. Then you have to divide by the
ID FSU.
5. It's 1 meter. And this is the length, okay? 5 dl. This should be equivalent to the
FSU.
FSU is, as Robert said, is 0.6 MPa. Then what is the initial approximation there? Meters? In meters, how much? you got?
I did mine. I used 0.65 for some reason.
We got nearly
I've
5
messed
points.
up somewhere there. I've got like, yeah, I've got like 9.7 meters. I need to find where I made a mistake.
Yeah, you just plug these values over there. You know, 5 value is 1 meter. Only the unknown is L, no? It's nearly, I think, say, just 6 meter. Okay. Then if that means initial, that means you are assuming 100% load is taken by the shaft. Okay. For this case, L over D ratio is 6, no? Your length is 6 meter. D is 1 meter. That's how this L over D 100% load is taken by the shaft. This is the first approximation.
Sorry, Robert, question. What do you get for your alpha factor?
I got 0.2 for alpha.
What did you get for QUC?
Which one? Sorry.
QUC? Like, you know how to find FSU, you just multiply by alpha and then beta and then by QUC, right?
Yeah. Mine was like 3,681.
Yeah, same.
Same. And then beta, did you get 0.7?
I got like 0.82.
Okay.
My beta is 0.82 as well, but your alpha is like 0.2. Mine is 0.3.
No.
What method do you find? Williamson-Pales or other one? I think you have found one. I think it should be nearly 0.2 alpha value.
Okay.
For this case, it's 6 and 0. Initial approximation. Then if I draw this one, then what was the EPO-ER ratio for your
38.
38? 38 means in between 50 and 25, no? Then you have to find this value and this value. This value is corresponding to 50 EPO-ER ratio. This value is corresponding to 38. 25. Then you have to interpolate the value to find the value corresponding to 38 EPO-ER ratio. I think it may be nearly 10%. Then the final length will be nearly maybe L over D means just like a 5 optimized length from this one, I think, if I draw correctly, nearly 5 point something, not more than 5.2, 5.4. And this rock socket pile, the base cleaning is essential. If assigning some fraction of load to base, your base should be clean, but it's very difficult process. You cannot get every time a clear base. There may be debris inside the borehole. Therefore, it's good to maintain a majority of the load to the shaft in the rock socket pile design. In this case, in this Melbourne area, we cannot rely on that base. At least more than 90%. If it is going to the shaft, it's good. And one other thing, if you get you told that EPO-ER ratio is 38, no? I
Yeah.
think it should be nearly 40 if you
I
after
got
you do
41.
that correction. Yeah.
Oh,
40.
yeah.
For
That
the
was not
rock
that.
mass, right? So for the total settlement, it's just delta V plus SE1.
Yeah, that's the thing. That
And
by
for
later
delta
when
V,
you will get that this equation, that rho plus that PLOA is even.
so delta V is the loading, also the load plus the negative skin friction.
For this one, yep.
Yeah. So we still include the skin 216 as well.
Yeah, settlement long term, no?
Yeah. Okay.
Whatever that 8,000 plus 216, as Jani said, the negative skin friction should be applied in the serviceability as P.
Jayani, what do you get for your total settlement?
I'm still doing the influence factor. What did you get for that?
I
Point.
got 1.14, but I don't know if I'm right or not for the influence factor. I could be wrong.
Just need to follow the chart.
Yeah.
That means
It could be 0.2.
Yeah, we are all back. Have a little bit rest. Take a couple of minutes break before we start our final session. How did you go, Udaya? Unmute.
yeah, I went to room 1 and 2.
Yep. Are they okay?
I think room 2 they calculate up to the settlement. They
Okay,
calculate
that's-
the settlement. Yeah.
That's really
And
good.
the room 1 I went at the middle. I think they were at the initial stage.
Yeah. I when I was there, I just only with them for the structural, check. Then they started the shaft resistance and all those sort of thing. And so they
Yeah, I think in room 1, 2 guys did full problem.
I think it's good they would have shared with each other.
Yeah.
Yeah, this was not one of the difficult problem, but only I think you have to keep your eyes open. This design can, I think, we need to make sure one of the thing I like to clear everyone. Okay. Can you put your videos on, probably? That's really good. This will be an interactive one. We just like to discuss everyone in presence. That's really good. Yeah. It's really, really good. So one of the thing, what I like to point out before we go and discuss our output, always think about when you are designing rock socket pile, remember the pile is going to take significant load and there is no chance for you to have any, what you call under design, or over design. That's why you have to put your best thought to determine the properties of the rock, to apply maybe a couple of methods. This is the first time I am trying to, emphasize that, well, one method is not good enough. When you do rock socket pile design, try maybe 2, 3, 4 methods, and try to see the best out of it, because the redundancy is very less. If one pile is failing, the whole structure will be under threat, because each of the pile takes significant load. And we cannot put a group pile like easily. We can have 2, 3 piles. Think about your project